This is the next video in a chapter on electronic structure and periodic properties. We have just spent several videos talking about light as a particle and light as a wave and how it can operate as both, but we promised we were going to talk about electrons, so we are finally going to talk about electrons in this video. So, what does all the stuff we've been talking about have to do with electrons? What does the quantization of energy, also known as quantization of light, have to do with electrons? So the spoiler is that the reason we have to relate quantization of energy with electrons is because the energy of electrons is also quantized. So we can use that information to help us adapt our view of the atom. Remember the last time we updated our captain's log with what an atom looks like, we said an atom has protons and neutrons inside of a nucleus in the very center of an atom, and the rest of the space is mostly empty except for a few electrons swirling around. And we used a sort of a planetary model saying that the electrons probably orbited around the nucleus similar to how planets orbit around the sun. But we need to add more information to our model about the energy of the electrons to help us understand why some elements react with some other elements. So there was some new science coming out at the time that Bohr made his model of the atom. And this new observation was about energy emission. So energy or light emission by hot objects. So when you heat a substance, it starts to get very, very hot. And you might notice that it starts to change color and it starts to feel warm. If you put your hand next to it, you can feel that there is energy being emitted. Energy is coming out of that hot object. And scientists were finally developing the sorts of tools that they could use to measure exactly what energy of light was coming out of those objects. So there were several different types of objects that they measured. And for some of these types of systems that they measured the emission of, the emission was continuous. And that's a word we know how to use now. So we know that continuous means that there's no limit to which values you can choose. Any value of the frequency or the energy or the emission is legal. So what this looks like to your eyeballs is white light. But what it looks like when you use a prism or a spectrometer is it looks like lots of different colors of light, lots of wavelengths. So we're going to enjoy ourselves and use rainbow colors to illustrate what this spectrum looks like. So what I'm drawing is called an emission spectrum. It's a picture of all the different wavelengths of light that are emitted by some sort of a hot object. And this spectrum is continuous. Every wavelength is represented. So it's a continuous spectrum. Okay, that was fun. So this fit well with the classical mechanics version, but there are other objects which had a different kind of spectrum, and that spectrum was quantized, which is a word we also know how to use. So that meant when you heated up these other types of objects, they didn't produce white light that was composed of lots and lots of different wavelengths. They produced light that only contained a few specific values for the energy of light. So I'm going to draw the spectrum for hydrogen. In particular, the visible spectrum for hydrogen consists of one line in the red, one line in the blue, a line in indigo, and a line in violet. And these spectra look pretty different, right? One of them looks like a full rainbow, and one of them just looks like 4 individual lines. 410, 434, 486, and 656. These are the visible lines that hydrogen produces. So this is a very different looking spectrum than our continuous one. So this kind of a spectrum is sometimes called spectral lines, or a line spectrum. So this was another issue of confusion at the time. Why would some hot objects emit a continuous spectrum, and why would some hot objects emit a line spectrum? And the difference was that the types of samples that produce these quantized line spectrums were elemental. They only contained one element, meaning that all of the atoms were of the same type. And so Niels Bohr decided that he should incorporate this information about the quantized energy into the model of an atom, because this was a feature that was showing up for atomic emission spectra. So the new information that Bohr incorporated into the model of the atom was the energy that belonged to an electron. So Bohr said these electrons that we previously said were orbiting sort of at random, they occupy specific orbits. They have particular paths that they follow. And each of these orbits has a specific energy. In other words, the energy of an electron is also quantized. There are only specific energies that an electron can have. And he tied this in with these quantized line spectra. He explained it by saying that the spectral lines correspond to energy differences, or energy steps. And these are the differences between the allowed energies for those orbits. And we can think about this the same way we thought about quantization at the beginning, thinking about it as shoe sizes. So the energy difference between the shoe sizes would be the difference between an 8 and an 8.5. Most of the energy differences for quantized shoe sizes is half a shoe size. So what this says is the energy of each of these different lines corresponded to the gap between 2 allowed energies for an electron orbit. So he changed the way that the model of the atom looked. So he said, okay, nucleus, still in the center, still positively charged. But instead of just drawing one circle to represent where all of the electrons are located, we can draw individual orbits or individual tracks that the electrons follow. Each of them slightly bigger and slightly further from the nucleus than the last. And we can number them. So we'll number the orbit that's the closest to the nucleus and the lowest in energy as n equals 1, and n equals 2, and n equals 3. And my picture has run out of space, but you can continue indefinitely with these different orbits. And so what Bohr said was he gave some information about what he thought the energies looked like. He said that at the center, closest to the nucleus, we had the lowest energy orbitals. So these are the most comfortable. Electrons are negatively charged. Let's add one. Here's an electron. They're negatively charged, and the nucleus is positively charged. So the lowest energy, most stable setup is for the negative electron to be very close to the positive center. So the closer the orbits are to the center, the lower their energy. And the orbits that are far from the nucleus those are going to be higher in energy. So you increase in energy the farther situated you are from that positive center. So we have this model. Let's try and make this model work for explaining this weird line spectrum for hydrogen. So let's zoom in on the top half of those orbitals so we can draw a couple more lines here. I'm going to draw a number of orbits, and we'll draw the nucleus at the center. You'll see that there are lots of different ways to draw these orbits. So like we said before, closest orbit to the nucleus is numbered 1, and then the numbers increase, and so does the energy as we move away from the center. And so with a combination of Bohr's model and Balmer's measure of these lines, what we found was that each of the lines corresponded to a transition between two of these energy levels. So the pink one is the lowest energy, 656 nanometers is the lowest energy in the visible. That one corresponded to the transition between level 3 and level 2. We looked at the blue line as the next highest energy. That one matched up with the transition between level 4 and level 2. And then the next indigo line corresponded to the transition from level 5 to level 2. And the next one to level 6 from level 2. So each of these different energies corresponded to the energy difference between some of these levels.